Everybody. My name is Jackie. I am the session chair for our next session. And we are about to get started for hours. We have all of our speakers in the room. So our session is titled Up and Coming Applied Statistics, and we have three amazing grad students here to speak to us about their current research and their current work in the field. Each of them will have about 10 minutes to give their talk, and then we'll have a couple of minutes for questions each at the end of their presentation. So first up, we have Maggie. Maggie is a fifth-year PhD student in statistics at Washington State University with a strong dedication to both research and teaching. Her studies focus on statistical scrutiny and AI classification, particularly in managing ambiguity through neural zones. Through her work, she strives to enhance the interpretability, robustness, and practical deployment of AI-driven decision systems, ensuring that statistical rigor remains at the core of modern machine learning applications. So I will give the floor to Maggie. And Maggie, let me know, are you able to share your screen with your slides?
Thank you, Jackie. Yeah.
Great.
Okay. So here, okay. Hello, everyone, and thank you for being here. My name is Maggie, and I'm excited to be presenting our research on neutral zone classifiers, a tool for improving the reliability of classification predictions, especially when uncertainty is high. I will share the motivation behind this work and the method we explored, key results from both simulations and real data, and we will see this work going next. Let's begin with some background. Artificial intelligence is deeply data-driven. It relies on statistical ideas from how the data is collected all the way to how models are evaluated. While it has grown into a transdisciplinary field, one key question still remains: when can we really trust a model's prediction? In 2017, Yu and Campbell introduced a helpful framework called PQRS, which stands for Population, Question, Representation, and Scrutiny. It's meant to guide responsible AI development. Population is about understanding where and how the data was generated. Question focuses on making sure we are solving a meaningful domain-specific problem. Representation asks whether our training data actually reflects the population we care about. And scrutiny, which is the focus of our work, is about carefully evaluating the model's outputs and assumptions. Now let's talk about accuracy. It's a common metric, but it can be misleading, especially with imbalanced data or high misclassification costs. A model predicting only the majority class might look accurate, but fail in practice. We do have tools like cross-validation, confusion matrices, and false positive or false negative rates to go deeper, but even these assume that the model has to make a decision every single time. That brings us to the central question of our research. What happens when a model is forced to make a prediction even when it is ambiguous? This is especially risky in fields like medicine diagnosis or fraud detection, where guessing wrong can have these undesirable consequences. So let's consider a motivating example, classifying adeno-associated virus used in gene therapy. AAVs are non-enveloped viruses with single-stranded DNA inside a protective shell. They are used as delivery vehicles for gene therapy, and the correct dosage depends on identifying the virus type. Misidentifying them can lead to ineffective treatment or serious immune reactions. The dataset we use come from solid-state nanopore experiments. Here, AAVs are passed through a nanopore under an electrical field, and the resulting current signals affected by their DNA content are recorded. Here is a representative 10-second segment of resistive pulse data corresponding to single DNA and double DNA AAVs. We use a pre-trained convolution neural network to classify these signals, focusing on distinguishing between single and double AAVs. From the 1,241 training observations and the 310 testing observations, the CNN achieves this decent accuracy, but 75 observations in training and 26 in testing were misclassified. That's an 8.3% error rate, and even though it is relatively low, the implications are high. Misclassifying a single DNA as double DNA could result in overdosing and potentially toxicity. And here is neutral zone comes in. Instead of forcing the model to classify every signal, we let it hold back for ambiguous cases, flagging certain observations as too close to core and introduce human in the loop for complicated decision-making. Dr. Jessica and others originally developed the neutral zone concept for two-class model-based classifiers where the population distribution is unknown and the conditional probabilities can be derived. But things get more complicated when we move to non-model-based classifiers like artificial neural networks, multilayer perceptrons, or CNNs. These models only output predicted class probabilities, so we can easily derive the class conditional distributions. That's where our methods comes in. We reframe classification as a hypothesis testing problem. To do this, we draw on two ideas. First, we use an oracle estimate called a DIBO to estimate the cardinality of each group. This helps us understand the overall class balance. Second, we adapt a concept from ranking and selection method known as the R-power method, which helps determine whether the top probability is meaningfully higher than the rest. Let's describe the basic ideas of the two methods. R-power focuses on the probability that the selected top R-test statistics actually come from the alternative hypothesis, not from the new. Assuming equal variance for the one-sided cases, RP has the following format. It depends on M0, number of observations in the new that we obtained through a DIBO method. Delta, effect size, M, total number of hypotheses tested, which is known, and R, size of top list calculated based false positive and false negatives. A DIBO is a technique developed for the normal means problem to estimate the proportion of true nulls. It uses an empirical Laplace transform of the test statistics. As t goes to infinity, non-zero test statistics contribute 0 and near-zero test statistics contribute 1 to the sum, giving us a proportion of how many values come from the null space. And we will walk through the full procedure in the following slides. Suppose we have n observations to be classified in two groups. First, run an algorithm of our choice and have the probabilities. To check whether a given probability is in a particular class, we perform two one-sided hypothesis tests. For each of the n observations, use the usual test statistic for proportions. From there, we set all negative test statistics to 0 and then calculate the DIBO estimator twice, when the first group is our null and when the second group is our null. Next, we average the estimates to find the cardinality for both groups. We then use this in the R-power to calculate the R0 and R1, how many in each group is reliably in the group. The n minus R0 minus R1 that are in neither groups are the ones that in the neutral zone. So the neutral zone depends upon our choice of false negative rate, which is defined as 1 minus Rp, and the effect size delta in equation for Rp. So returning to the motivating example, we apply this neutral zone idea with different false negative rate and effect size. For the training data with a true proportion of double-stranded DNA of 0.67, the IDWSDS estimator is 0.6. So as false negative rate increases, the neutral zone size decreases with a fixed delta, and for constant false negative rate, higher delta leads to a narrow neutral zone. And when the delta is 0.5, the neutral zone misclassification rate remains 1, while when delta is 2, it drops. We observe a similar pattern for testing data. What this shows us is that to capture all the misclassified observations, we would need to have a larger neutral zone or have more observations that were correctly classified come up as too close to core. And we follow this up by a simulation study to understand the choice of delta and false negative rates. In each simulation, 500 observations from bivariate normal distributions are classified using ANN and MLP models. We calculate the delta in this way and varied the proportion of true nulls and false negative rates from 0.1 to 0.9. So both classifiers show similar classification performance in general, and the IDWSDS method effectively estimate for moderate and high true negatives and become less accurate for low true negative. And in the case of true negative is 0.1, 0.2, the neutral zone misclassification rate using IDWSDS are 0, possibly because of extreme imbalanced conditions and high false negative rate levels. For moderate true negative, almost all misclassifications fall inside the neutral zone. However, as true negative increases, neutral zone misclassification rate drops below 1. So overall, our work fills out the gap of neutral zones for non-model-based classifiers, and our proposed method works better for balanced data and with a small effective size. One limitation we faced was with the IDWSDS estimators we used to estimate the null proportion. While helpful, they can fluctuate and introduce bias, which may distort the neutral zone. We are now looking into more robust and adaptive alternatives that perform better across different data conditions. Another major direction is extending beyond the binary classifications. Creating neutral zones for multi-class problems is still challenging due to the complexity of class boundaries in high-dimensional spaces. Thank you so much for your time, and I'd be happy to take any questions you may have.
Work, Maggie. Thank you so much. If there are any questions, yes, give some applause for our speaker. Thank you. If there are any questions, feel free to put them into the chat, and we can try to address some now since we have a little bit of time. I'll give it just a minute or two of empty space for people who might be typing. Okay, going once, going twice. All right, well, let's give Maggie another round of applause and thank her for her time. Thank you so much, Maggie. We appreciate it. Our next speaker on the docket is Weiwei. Weiwei is a doctoral candidate in the statistics program at Washington State University's Department of Mathematics and Statistics as well. Her research centers on the investigation on random walk null models for time series entropy analysis. Working under the esteemed guidance of Dr. Daryl DeFord, Weiwei aims to advance the understanding of randomness and complexity within time-dependent data. Prior to her doctoral studies, she earned her master's degree in statistics from Washington State University in 2021. So Weiwei, we're very excited to hear about your research. Let me know if you have any trouble getting your slides set up, but otherwise you have the floor.
Thank you, Maggie. Okay, let me share my screen. Okay, can you see my screen? Okay, great.
Yes, we can.
Okay, thank you. Hello, everyone. My name is Weiwei. So I'm so excited to sharing my work on divergence measures on distributions of ordinal patterns in time series analysis, and which I work with Dr. Daryl DeFord. So we will have 5 sessions in total. First of all, I will introduce the background of permutation entropy, and then I will talk about some examples for the examples of the permutation patterns to understand how they work in time series data from real life. After that, we will be heading to the main session, divergence measures, and I will discuss the theoretical stuff and applications of random walk non-models with uniform steps and normal steps, built upon the permutation entropy methods, as well as introduce the novel random walk non-model based on transition metrics inferred from the real world data. Finally, we'll probably also discuss the potential future network directions for this research. So first of all, imagine that you are trying to analyze the fluctuation of a stock market or the rhythm of heartbeat. This challenge is where permutation entropy emerges as a powerful tool for time series analysis. Permutation entropy is a very popular metric for measuring the complexity of time series, which has been widely has been introduced by the Dr. Bent and Dr. Pong in 2002. It has been widely applied to lots of areas like biology, economics, and physics. So this measure analyzes the patterns formed by the relative order of values within a short segment of time series data regarding with different embedding dimension. So the non-model are crucial tool for interpreting permutation entropy measures by defining a baseline against the permutation entropy of the observed time series. Dr. DeFore and Dr. Moore have proposed some random walk non-models to analyze the correlated financial time series data by using the Kobeck-Lipler divergence in 2017. And the permutation Jason-Shannon divergence also has been applied to evaluate the similarity in arbitrary time series by Dr. Zunino Absafter in 2012. For the convenience, I will just call those 2 divergence measures as scale divergence and JS divergence in the rest of the talk. So then you might be curious about what permutation entropy is doing in an empirical series. So now I'm going to show some examples of permutation patterns. This is a short time series example with 6 values, which from x1 to x6. So when the permutation pattern only look at the order of values within a short sequence. So the blue color sequence with x2, x3, x4 represents the permutation pattern of 3, 1, 2, when the embedding dimension here, which n is equals to 3. While when n equals to 4, then the colored subsequence shows the pattern of 1, 2, 4, 3. So then we might be also interested in what is about the complex time series, right? So this is the Apple daily stock closing price data from 2019 to now. This is the distributions of the permutation patterns, which is actually showing the frequency of occurrence for each pattern when the embedding dimension here n equals to 3. This is when n equals to 4, when n equals to 5. So, but how do we calculate the permutation entropy? So this page shows the mathematical expressions for both standard the permutation entropy and the normalized one as well. So now let's delve into the KL divergence and JS divergence. We usually use those two divergence to quantify the similarity between observed and expected permutation patterns. These are the mathematical expressions for the KL divergence and JS divergence. And actually, the JS divergence is the symmetric version of KL divergence. And while the random walk is defined as the cumulative summation of RID continuous random variables, which we can see these variables are the steps. And the permutation patterns within this like random walk occurs with some like positive probability. The expected distribution of permutation patterns is not uniform when the n is greater or equal to 3. So in our study, firstly, we have like explored the random walk non-models with two cases. One is the uniform steps and the other one is normal steps. Under the case of uniform steps, we assume there are like two ID random variables, x and y, that are all uniformly distributed on a range from A to B and E to F respectively, where the A and E they are negative values, and B and F they are all positive values. The difference between for both intervals they are all one unit, yeah. And embedding dimension we assume here is like 3. So next I'm going to show you how the random walks work based on uniform steps distribution, which is distributed from -0.4 to 0.6, and with like a different embedding dimensions. So here, when n equals to 2, there will be only 2 patterns up or down. So showing in the left points working animation, where the blue points means going down and the red means going up. The random walk looks like the right-hand side animation after like 100 time strokes. And when n equals to 3, okay, this one. So when n equals to 3, instead of like having all the steps in a line, it getting onto a like 2D plane with the points going corresponding to the patterns. There will be like 6 patterns in total. And the geometric version has been like represented in a 2D square plane, which is on the right-hand side. And here is showing how the random works becoming based on the steps after like 200 time stroke and the changes of the probability for every pattern. And this page is showing like the 3D plane, which is represent the integration regions when the embedding dimension is 4. So this work is much more complicated than other two cases. So we worked out these like with these really complicated formulas. Now we have like those sort of like theoretical expressions. What we can do with these? So okay, there is something we work on like to apply those formulas to. So the table shows the convergence expressions of JS divergence between two random walks that are defined by like x and y. Why the set faces here in the like third cases is because of these. So it's very complicated to put them on the same page. Okay, so, and this was the work for the uniform case. Next, you probably have questions about like what is about like coming up with other distributions. So is there also a convergence trend for the JS divergence of permutations in random walk non-models with normal steps? The answer is yes. The basic assumptions and settings are similar with the uniform step cases. And random walks generated with the ID normally distributed random variable y, and we successfully found the expected distributions of permutations with like embedding dimension of 3. And so we can see, and those formulas we can see they're all related to its positive probability p, and they can be kept. So yeah, And here are the two random variables, X and Y, which are normally distributed with like a mean 1 and variance 1 and mean 2, variance 2 respectively. And then we define the two random walks Z and W based on those two steps. The positive probability for them are PZ and PW. And now we are considering the scenario when embedding dimension length is 3. Here is like something we work on to apply those formulas to, like above. And this table shows the convergence expressions of JS divergence between the two defined random walks non-models. So now we have talked about like the theoretical findings and results for both cases. Let's look at the generalization. These slides shows the example of the Apple stock closing price and when the embedding dimension is 4. So this plot here is representing the permutation distributions from the empirical data. And here is the histogram of steps, which is like almost bell-shaped. This is the random walk non-model with uniform steps. And while this is for the normal steps. So it's obviously we can see that the observed values match the normal non-models much closer than the uniform one. Then we can tell that the observed steps from empirical data affect this result. Okay, so the previous approaches here focused on learning the step distributions and modeling to those. However, we can also capture the similar type of the data by studying the Markov chain on patterns. And that can be like introduced by these like random walks. So let's see, this page shows the examples of Markov chains from patterns for the patterns of when the embedding dimension is 3. So the left Markov chain represents a transition among all the possible patterns. And well, if we are like add like a permutation pattern of 1, 2, 3, so the next step is just taking the last 2 plus the next one. So then there are like 3 possibilities for the next pattern occurs. If the next one is above these 2, then we will get another 1, 2, 3 pattern. If it's in between, then we got like 1, 3, 2 pattern. Or it's below, then we get the pattern of like a 2, 3, 1. The right plot shows exactly how it works. And then these are showing the like the edges like come with the probability. And the stationary distribution based on this transition is shown as the histogram on the right. So we could have like more sense about like how this works from like this animation. You can see the color changes for each pattern, and this draw is like is over like 200 times. Okay, all right, so I have just like talked about like all the stuff and uniform and normal stuff, normal case. And we also mentioned about like the Markov chain approaches. So here is this page showing the multiple comparison of the JS divergence for observed Markov chain and the random walk non-models with the empirical data. So we can see the approach of the Markov chain does better than the other 2 approaches. And these data here, we are only using from like a financial area. So we are still like working on like scaling up to bigger dimensions to see how it changes. Okay, so here are the visualizations of JS divergence for Apple stock and United Airlines stock data. So for both of them, we can see, especially for the United Airlines, there is a spike in 2020s, so which is around like a COVID time period. So, and for the other 2, we didn't see like a very significant pattern, but we can see there's small like changes in like some like years, which has like a big event happening that year. Okay. And this is the the generalization we can see from the stock data. And this is like some preliminary work, but one of these like things we are trying to understand is, can you decluster the stocks effectively based on their pairwise JS divergence between them, rather than just like studying one of them at a time? So we did the pairwise comparison for S&P 500 stock data and computed the JS divergence. And here is the density for the left-hand side. The one is the density for each sector based on the symmetric JS distance metrics from like the empirical data. And the right-hand side, this visualization is the random work with learned transition probability from the like empirical data. And so we also apply these distance metrics to the backbone networking using lens. So look at like so we can see the left-hand side here. This is the MDS plot for all the sectors, which shows lots of like overlaps here. However, if we look at like a specific sectors, it's much clearer to distinguish them. You can see some like it's with like a much clear like boundary between them. So, however, if we are looking at like this is something we are still exploring and trying to figure out how to best use this information. Yeah. And if you have any questions, please let me know. Then I will just move on to, this is some like potential directions for the future work in this field. So like, is there like a transition probability when given a stationary distribution, and the inverse question as well? Or can we find the bounds of the mixing time between the empirical distribution, the permutation entropy the empirical distribution and the stationary distribution based on the Markov chains methods? So maybe we can using the coupling Markov chains, or also we can study the random walk non-models with other steps rather than just the uniform and normal steps. Yeah. And so here is like for the further reading on this topic, please refer to the following resources cited throughout this talk. And thank you. Please let me know if you have any questions. I'm more than happy to answer.
All right. Thank you so much, Weiwei. That was awesome. Let's go ahead and give Weiwei a round of applause as well. There are a couple of questions in the chat that I want to make sure get answered. Weiwei, I think you might be able to see them as well, but I'll read them out loud so that everyone can hear them. Let me know if you need me to repeat them, okay?
Okay, so we have a question. Let me see.
So the first question from one of our attendees was a clarification. How do you obtain the steps from the financial data? Are the steps the returns? Then also, how do you obtain the first row, first column of plots found in slide 26 from the data? So a little bit to break down, but.
Yeah, let me go back to the pages. So It's like page 26. Wait a sec. This one. So first of all, let me see the first question. How do you obtain the steps from the financial data? And other steps, the returns. Okay, so for my understanding for your question, it's like you mean obtain the steps. It's like how do you store the steps to put them in the visualization? Or but the way I'm doing here is like, because we have like the series like visualization for each stock data. So what we do is like, because this is the case for like, for example, this page, the embedding dimension is 4. So we're only looking for like points. For example, the starting points is to 1, 4, 6, or 7. And we only look for like the first 4. and we check like the orders of those 4 values, then it becomes like the patterns, right? And then we are moving on to the second pattern, which is starting for the second point and go on. So we are like store the patterns, like the occurrence for each pattern in this way. Yeah. And let me answer another question. How do you obtain the first row and first column of the plot? First row and first column. So you mean the first one?
I think so,
this
yes.
plot here is showing the probability of the occurrence for each pattern. Yeah, is that more clear to you? Okay. Let me go ahead to the second question. What's the task?
I'll read out the next question for the audience as well. The question is, was the task for the financial application to determine if stock prices follow a random walk using permutation test methods?
So this is really a good question. So the permutation methods here, you can say in that way, we can say, because usually the time series data, especially from the chaotic arbitrary data, those kind of like series data is very complex and it's really hard to estimate or like do some forecasting, especially for like a price data. So for the permutation entropy, it's kind of like a very useful tool. So we are not like starting all the series data itself. We are starting for the patterns, like seeing how the patterns like within like a short segments of like subsequence to see how they like change. And in that case, then we can quantify, see, for the random walk model here, like a random walk model, we are going to like, so that in that case, we have like a baseline and to comparing with the empirical distributions or like series that from real life, and using those data to comparing like this baseline, so that we can say, oh, maybe this like a time period, it has some changes. And for like other one, we have other. So in that case, we can find like have a like an insight to see the changes for the data, which is very complex to analyze. Yeah, if that answers your question. And it's not kind of like not determined, because it's really hard to determine. It's like following, but these questions go so like actually is more matched to the next like exploration, because we are like now working on some like other like methods to say if we can to detect this like distribution as like a random walk or as like some distribution which is not a random walk. Yeah, but this one is, I didn't put these methods in this slide because as we are still on the exploring process, but good catch. Thank you.
Thank you, Weiwei. I appreciate that. Okay, I did notice we had a hand raised earlier from Claris. I just wanted to confirm whether or not you got your question answered. If you could just give me a quick thumbs up if you got it answered, that would be great. If not, feel free to raise your hand again and I will have you unmute, or you can post your thing in the chat. Okay, great. I see your thumbs up. Thank you so much. Any other questions for our speaker, Weiwei? Okay, great. Let's give our speaker another round of applause and thank her for her time. Thank you, Weiwei. You did wonderful. And we're going to set up for our next speaker now. So our next speaker on the docket is David Rice. David Rice is another one of our graduate students at Washington State University. He is a fifth-year PhD student studying statistical science. And his current research focus and specialization is in tensor methods within statistics. And And also a cute little snippet, in his free time, he likes to make homemade pizzas and loves to go on runs. So David, we're excited to hear your work. If you have any trouble sharing your screen or anything, let me know. Otherwise, the floor is yours.
Okay, perfect. Thank you, Jackie. I apologize. I am a little bit sick right now. Here we go. Hello, my name is David. Today I'm going to be talking about Kolmogorov-Arnold networks and tensor decompositions. So this is new preliminary work that I kind of started this year. And so I just wanted to take this opportunity to talk about it because I think it's pretty cool. So we start out just with the problem. Say we have some scalar value yi, of which we want to predict based off of some xi, where xi is in Rm. Each observation has like m columns. We want a way to fit some flexible nonlinear function f hat, where we assume that our f is smooth and differentiable. So what we can do is we can lean on a relatively new development of something old, which is the Kolmogorov-Arnold representation theorem, which is up here. And so it basically says that if f is a continuous function, it can be represented as a finite combination of continuous univariate functions. Here we have this phi qp, which is going to be a univariate function applied specifically to the pth column of x. And then we have the capital phi q on the outside, which will kind of take which will map a real number to a real number. And this can be used to represent our function. And so we note that unlike the multi-layer perceptron, where we would have some ReLU function in here, and then some like combination, nonlinear combination on the outside, we are simply having some nonlinearity on the inside, and then adding them together outside. And so another way to look at it is we have our inputs in the x here. We say I'm going to take my inputs and in order to map them onto my neurons, I'm going to fit some nonlinear functions. I'm going to for each of the x values. Then I'm going to add up the evaluations of these nonlinear functions to get to this neuron. Here, every line is going to be some nonlinear function, usually fit by B-spline. And the nodes here are going to be the summed linear combination of values from these nonlinear functions. And so to formalize this a little bit, we say let B of k, where k is in ND, be a set of basis functions. Here, if we're thinking about like a set of spline bases, k will be the number of coefficients needed. For each of our different layers, we have AL is going to be an NL, where NL is the number of nodes in this layer. NL plus 1 is the number of nodes in the next layer, and ND is the number of spline coefficients needed for each of the layer. We'll denote a parameter tensor of the elf layer. And so we can think about each activation function as the sum from k equals 1 up to ND, where ND is the total number of spline coefficients. We have this the spline coefficient element times our basis function. So we have a representation function for the input from node of index P of layer L to the node index of Q on layer L plus 1. And so this function will be the value that gets you from here up to here. If we want to represent, the actual value of the node on the on the next layer, we can define z L plus 1 Q index Q to be the sum going from, we have the pth node, and we want to sum up all of the pth nodes up to NL to get us the combination of values for the next node input. So here we have the spline coefficient applied to the previous input layer node at at index P, and we're going to multiply that by a spline coefficient, sum up across all of the different spline coefficients for a given node, and then sum up across all of the individual nodes, feeding specifically to the qth index of the next. So one problem that this has, which a lot of neural networks have, is that there are a rather large number of parameters to estimate. So what we want to do is we want to think about reducing the number of parameters through tensor decompositions. And the question is, how can we do this in a principled way? Well, what we can do is we have this AL, which is going to represent the tensor of coefficients at layer L, which is going to be NL, the number of nodes in the current layer, by NL plus 1, number of nodes in the next layer, by ND, the total number of tensor coefficients. And we're going to impose a Tucker decomposition or some other tensor decomposition on it. So for example, for a Tucker decomposition, we see we can represent this tensor X as the core tensor matricized along the first mode times the QNL tensor matricized along the second mode times the QNL plus 1 tensor, finally matricized along the third mode times the QND factor matrix. So here QNL, QNL plus 1, and QND are going to be these matrices. And this core tensor is going to be hopefully very small. And so if the core tensor is relatively small compared to the initial X value, the intuition is we should have a drastic reduction in our parameter counts. So what does this look like? You know, when would we be concerned with this? Well, if we reduce the dimension too much, we might end up running into some error. And so for Tucker decomposition and tensor train decomposition, the error due to approximation can be bounded using the singular values of the matricizations. If I were to take my X here, and I were to take all of these strands, stack them up, and look at the singular values, the decomposition into Tucker or tensor train will implicitly truncate some of these singular values, and the error is going to be bounded by the truncation. And so we are able to bound it, because we're able to bound it by the truncated singular values. If our singular values decay to 0 very rapidly, we're still able to approximate very well. And we can do this layer by layer, but we can also, for a larger dimension reduction, fix the number of neurons in each layer. N1 equals N2 equals NL equals N capital L, to have a tensor of shape NL by ND by LA, which is the total number of layers. And so we can think about this through a motivating example. Here we're going to think about predicting breast cancer malignancy based on the tumor characteristics. Here there are roughly 30 characteristics with size and shape and maximum width being some of them. What we're going to do is fit a Kolmogorov-Arnold network with layers 30, number of inputs, by 30 by 30 by 1, here being the number of nodes in the hidden layer, number of nodes in the hidden layer, and the output, which will end up being either a positive diagnosis or a negative diagnosis. From this, we see it reaches an accuracy of 98%. However, we see this is a rather large number of parameters, and the model is likely over-parameterized. So what we can do when thinking about this is we can think about on the first layer, we matricize our tensor of spline coefficients, which is going to be 30 for the number of inputs, 30 for the number in the next node, and then 5 being the number of coefficients for our splines, and observe the singular values decay to 0. On the right, we have the singular values of the layer 1 matricizations. We have this red line at y equals 1, and so we see a decent number fall below it, and we see the bulk of the singular values are quite a bit higher. For mode 2, we see a similar trend. For mode 3, the singular values are all reasonably large, and so we decide not to trim along that mode. So what we're going to do is we're going to truncate based on this threshold. And so we define our core tensor with a rank of 15 by 19 by 5. And what this has done is it has reduced the parameters of the first layer from 4,500 to 2,895. When we rerun the prediction on the test set from this recomposed tensor of coefficients, we maintain an accuracy of 0.97 with a relative reconstruction error of our tensor of 0.1328. Similarly, because we have a 30 by 30 by 30 by 1, we can think about Kolmogorov-Arnold network. We can think about taking the entire set of hidden layers and converting it into a tensor as well. So we repeat the process. We consider the set of hidden layers of shape 2 being the number of layers by 30 by 30 by 5. We truncate the coefficient based on the thresholds, resulting in a Tucker decomposition of rank 1 by 19 by 24 by 5. Here we see the second singular value for mode 1 being the number of layers falls below the 1 threshold. We see several of the values in mode 2 and mode 3 fall before, and again in mode 4 none of them meet the threshold. So here we have reduced the coefficient parameters of the network from 9,150 to 2,430. Again, we're able to maintain an accuracy of 0.97 with a relative reconstruction error of 0.9. So, this is relatively preliminary research. This is something I started working on this year, and I'm just kind of excited to talk about. But due to the drastic cut in parameters, we wish to introduce some uncertainty quantification through perturbation of spline coefficients. We hope to determine some bounds on the error due to approximation. We already know that we can bound it through tensor decomposition. We can bound it through the decomposition based on the singular values for each layer. We can do it for several layers, but we want to see how the relationship between doing the decomposition on single layers versus several layers. When can you choose to do the entire network-wise decomposition? And lastly, we want to apply this method to material science surrogate modeling. We see that in a lot of cases, having an easy to fit low parameterization neural network to predict stuff that would be done through physics modeling is a very popular application. And with the controlling of the ranks for the tensor decompositions, it allows us to get some kind of lower versus higher fidelity in our modeling. But that is all I have for today. Thank you.
Great. Thank you so much, David. I appreciate it. That was an awesome talk. Let's give David a round of applause. And now we'll open it up for any questions for David specifically. You can either submit your questions directly in the chat or through the Q&A function. Appreciate all the applause coming through. Thank you guys so much. I'll still hold just one more minute for anybody who might be typing. Okay. Great. Well, thank you everybody for coming to see our speakers today. Thank you to our speakers, David, Weiwei, and Mengqi. You guys did wonderful. And if you guys have some time, whatever time zone you're on, there are events for the next 24 hours, right? So go and check out the different events on this Sched app and see what's next up. So thank you so much for coming and hope you stick around for the next session.